Do you need to optimize quality and throughput? This is the focus for the project Smart Assembly 4.0 within Winkvist Laboratory, funded by the Swedish Foundation for Strategic Research. Today, industry is facing tough competition on quality, cost and sustainability. We see trends with faster algorithms, increased computer power, increased amount of data. This together with increased connectivity is taking us from simulations based on historical data to digital twins that allows for real-time control and optimization. This also allows us to move from mass production to more individualized production. In the project Smart Assembly 4.0, we have the vision of the autonomous, self-optimizing, robotized assembly line, which maximizes quality and throughput by a sensing, thinking, and acting strategy. The main question we ask ourselves in this project is, what if scan data of individual parts were available in line? Let's assume an assembly cell where two parts are coming in, are put in a fixture joined with, for instance, spot welding by a number of robots to form a sub-assembly. If we had the full geometries of all individual parts, for instance by scanning, we could perhaps sort and match the parts in a clever way, adjust the fixtures to compensate for the part errors, optimize the joining sequence to compensate for part errors, arrange some kind of feedback loop to capture the difference between simulation and reality. Let's look at this setup in a virtual demonstrator. During design and pre-production phase, we do initial locating scheme optimization, variation simulation and inspection preparation, all based on historical data. During production, we scan the parts. Based on the scan data, we can do selective assembly to find the best combination of parts. We put the parts in the fixture. We can then optimize the position of the locators and the clamping sequence. We can optimize the position of the weld points and the spot welding sequence. We can distribute the work between several robots to balance the workload. And we can scan the welded sub-assembly, we can do root cause analysis, and we can use machine learning to refine our models. To reach the vision and the goals put up for the project, the work is conducted in 5 work packages. Number 1, geometry data capture. Number 2, geometry assurance. Number 3, automatic robot programming. Number 4, learning and adaptation. And finally, work package number 0, the system level demonstrator. Now we will go through the different work packages and explain a little more. In work package 1 and 2, we focus on improving the geometrical quality of the assembly by reducing variation. In order to improve the geometrical quality of the output of our assembly cell, we have developed 3 different real-time geometry assurance strategies. All of the strategies are based on the idea that we have scan data of all the individual components coming into our cell. In the first strategy, selective assembly, we use genetic algorithms to find the best combination of individual parts, resulting in around 40% improved quality. In the second strategy, locator adjustment, for each pair of parts we adjust the locators in the fixture to compensate for the errors in the part geometries. This results in around 60% improved quality. In the third strategy, spot welding sequence, we find the optimal spot welding sequence for each pair of individual parts. This typically results in around 30% improved quality. We have tried these strategies on a number of different assemblies with similar results. What strategy to use is of course depending on the actual situation. One strategy may be more easy to apply and more cost efficient than the others. There is often no use in combining the strategies since the strategy applied first will be the most dominant. In work package number 3, we focus on automatic path planning. The geometry assurance activities that we just saw, selective assembly, locator adjustment, and sequence optimization, will for sure effectively reduce the variation in the assembly, but at the same time create a manufacturing challenge in the station. Unique geometries and individual motions for each assembly will require almost real-time generated robot programs without any chance for touch-ups. To resolve this challenge, we have in Work Package 3 developed 3 powerful enablers for automatic programming of assembly stations. Number 1, fast and robust path planning. Number 2, dress-pack-friendly motion generation. And number 3, automatic optimized coordination. The digital twin may, however, differ from the physical reality in our assembly cell. Consider, for instance, a locator with an error, not represented in a digital twin. To compensate for this, we mitigate such locator error within about 40 assemblies through feedback from the physical space. To do that, we slightly perturb the locating scheme, we measure quality through scanning, we update the locating scheme by optimization, we repeat these steps until quality is within a target range. We have seen with case studies an improvement of up to 75%. The goal of Work Package 0, our system level demonstrator, is to integrate the software components developed in the other work packages into a modular system and to validate and demonstrate the results. In addition to the generic components in the Smart Assembly 4.0 core, a case handler encodes specific information about the scenario at hand. For communication and data transfer between components, Apache Kafka message bus with JSON messages was chosen. It enforces a modular architecture, parallel execution, allows the different components, including hardware drivers, etc. in the real cell, to run on different platforms. The Kafka bus is widely used and has proven high performance, is robust and scalable. Several digital twins are used by the Smart Assembly core to simulate the outcome, optimize and make decisions. During the project, we also emulate the reality to the level of detail necessary for demonstrating and validating the solution. In the project Smart Assembly 4.0, we address the vision of the autonomous, self-optimizing, robotized assembly line. We have seen that we can improve geometrical quality with up to 60% by using our geometry assurance strategies. We address automatic robot path planning and the difference between the real and the digital world. We have around 40 publications related to the work in this project. In the list you can see a few of them. Thank you all for listening.